Hello. In this video, we are going to discuss how we formulate linear models, how we sort of write down linear mathematical models, given a sort of, presentation of a problem in non-mathematical language, using a sort of type of problem you probably have seen sort of starting fairly early on in your mathematical education. A second follow-up video will go through a wide range of different numbers of types of models in more detail for anyone who wants as much extra practice as they need. I'd like to sort of first of all start off with a framework of how do we solve problems with mathematical models and what are the basic steps. We can kind of break down solving these kinds of problems into three primary steps. Formulating the model, where we think about what the variables in the model need to be, define what they are so we know what the symbols in our equations mean, and then write down one or more equations, most often more than one, that capture all of the detail in the problem. The goal of a mathematical model is to write a set of equations that really describes as much as we possibly can about the problem, so that we're able to, our solutions are able to account for everything. Only after we've written down what the model should look like will we really start to think about how to solve it. It's hard to really address how do we solve a problem until we see what equations we have, what do they look like, what their form is. At this point, we start to think about what are we really trying to find. Depending on the type of problem, what we are looking to find, what a solution should be, may be slightly different. Once we know what we're trying to find, then we think about how might we find that problem, or that answer. After making the decision of what we're trying to find and how we're going to try to do it, then we go on to the third step of actually trying to solve the problem. Solving the problem has first of all, the process of finding the mathematical solution. Once we have a mathematical solution, we're not done with real world or pretend real world problems. We're not really finished until we have taken our mathematical solution and reinterpret it back in the context of the problem. Right? Now, we're going to discuss a lot about the model formulation part. We'll discuss at this stage, for the problems that we go through in these examples, how we might solve it and actually try to solve the problem. But how we actually go through and solve a problem, there's a tremendous range of different types of approaches. Algebraic manipulation, using calculus, graphical analysis, estimation, iteration, recursion. These are all things we'll be discussing more as the course moves on. What we will be learning moving forward is a whole ensemble of new methods, a whole toolbox of methods from linear algebra that can be used for certain types of problems, in particular linear problems. I think the best way to introduce or to sort of explain this process is to work through this with a kind of problem that's easy to understand, you've probably seen before and worked through before. We're going to try to solve this problem in kind of a systematic way to demonstrate how solving mathematical problems really can, problems with mathematical models really can be done in a much easier way, more straightforward way if we have a framework for thinking about it. We're going to explain the framework with a simple, easy to understand problem. The classic kind of word problem that you might have seen in your early introductions to algebra in school. The problem is presented here. Miguel spends $7 to buy 6 apples and 6 oranges. Liz buys 2 apples, 3 oranges, and a mango for $4. Wei buys 4 apples and 3 mangoes and spends $5. If this is the information we have, how much do apples, oranges, and mangoes cost? Let's walk through the problem systematically. Formulate the model by defining the variables and then casting the information into a system of equations. Think about the solutions. What are we trying to find? How might we get that answer? Then execute. Solve the mathematical problem and then interpret that answer in terms of the original problem. So let's walk through each of these simple steps. Okay, what are the variables of this problem? In many cases, the majority of problems, variables are the unknown parts of the problem. This isn't always the case. In some cases, some of the so-called unknowns might be best represented as symbolic constants. But in this case, all of the there's a limited number of unknown things. They're all of the same type. They're the cost of each type of fruit. These are the variables of the problem. Make sure we define them clearly. Let X be the cost of apples, Y be the cost of oranges, Z be the cost of mangoes. By writing this down clearly, it avoids any confusion at the interpretation point, interpretation step. We know what all our variables mean. When we speak of cost here, we're going to represent each of these as a cost per fruit because of how the problem was presented. We were given numbers of purchased items, and so that's how we are going to phrase the problem. Once we've done that, we can write down a system of equations. We summarize the information provided here by taking each person's purchase and writing down one equation associated with that. So Miguel spends $7 to buy 6 apples and 6 oranges. That's represented by 6 times X, the cost of an apple, plus 6 times Y, the cost of an orange, has to equal 7. All right. The second individual, Liz, 2 apples and 3 oranges and 1 mango for $4. 2x plus 3y plus z, 2 apples plus 3 oranges plus 1 mango, $4. We do the same thing for Wei, 4 apples and 3 mangoes, 4x plus 3z costs $5 equals 5. These 3 equations summarize all of the information here. There's no more information in the problem. There's nothing else we can write down. Our model is complete. This really is our model. Defining variables, system of equations. It's a mathematical model that represents this problem. So what are we trying to find? We're trying to find the cost of apples, oranges, and mangoes. That is the values of x, y, and z that make all equations true at the same time, if such a thing is possible. Right? There's an implication that this problem does have a solution, since it says that this actually happened, but we should always be aware that not all problems actually have solutions. So how might we do that? Well, we have a system of equations. We want to find values of x, y, and z that make all of these true at the same time. We can do this, find these by doing a set of algebraic manipulations and substitutions until we get to the answer. So how do we do this? I've moved our system of equations over here just as a reference. And I'll sort of I've highlighted the steps we're going to take: 1, 2, 3, 4. So let's sort of walk through these, and I'll explain a little bit about my logic here. If we look at this system, we see that there's two equations that only have two unknowns. X and y in the first equation, x and z in the last equation, whereas the middle equation has three unknowns. Equations with two unknowns are easy to work with. We can always rearrange them to express one variable in terms of the other. Right? And so our strategy is going to be to try to express one of these variables in terms of the other, one of these variables in terms of the other, and then substitute those in to this middle equation so that we only have one variable left. The common variable in equations 1 and 3 is x, so that's the one we're going to try to sort of express everything in terms of. So we start with the first equation, 6x plus 6y equals 7, moving the 6x over to the other side and then dividing by 6 gives us y equals 7 minus 6x over 6, an expression for y in terms of x. We can do the same thing for the third equation, 4x plus 3z equals 5, move the 4x over, divide by the 3, z equals 5 minus 4x over 3. Now we have y in terms of x, z in terms of x. We can take our third equation, 2x plus 3y plus z, and substitute in y and z. We write out that, simplify by combining all of the terms that have x's, and those that don't have x's. So just to sort of walk through that, 2x for the terms that have x is a 2. 3 times negative 6x over 6 is negative 3. Plus 1 times negative 4x over 3 is negative 4 over 3. These are the terms that have x. Terms that don't have an x, none in the first piece. 3 times 7 over 6 is 7 over 2. 5 over 3. Those are these pieces here. This 2 minus 3 minus 4 thirds is negative 7 thirds. 7 halves plus 5 thirds is 31 sixths. Moving this piece over gives us negative 7 thirds x equals negative 7 over 6, which means x must be a half. Once we have x, now we can go and plug that value back into our expression for y and our expression for z. And x equals half gives y equals 7 minus 3 over 6 is 2 thirds. and z equals 5 minus 2 over 3 is 1. We have an answer, but only a mathematical answer. Remember that the last step is to translate that back into the original form, our model, our mathematical system, our interpretation. If x equals 1/2, that means apples cost half a dollar, 50 cents, or 2 for $1. Oranges cost 2/3 of a dollar, 66.67 cents, or more easily represented as 3 oranges for $2, and mangoes are $1 each. All right. Hopefully, so one thing that we notice with this is that with even a relatively simple problem, an incredibly simple problem, you might say, the execution step can get tedious. The algebra can get a little bit algebraic or numerically messy. Fractions pop into things. It's easy to make mistakes working through things by hand. One of the most important applications of linear algebra is that it provides a set of robust methods, and what we're going to learn what some of these methods are in this course, that can be used to solve any problem of a certain type. Right? And the primary advantage of that is that when you have a method that can always be used to solve a certain kind of problem, you can write that method into a computer program that can then let a computer do all of your work for you. Right? These methods, however, can only be applied once you've taken a problem and are able to formulate it into the right type of mathematical model. Hopefully, this very simple problem gave you a flavor for how you go through that process for a given kind of problem. More complicated problems, questions, are more difficult or can be more difficult to formulate. In the accompanying worked problem lecture for this, or video for this, I'll be going through a series of problems of varying difficulty, working through the same kind of problem, formulating a model, thinking about the answer. Can we figure out what the answer is for a number of different classes of problems, many of which we will be revisiting multiple times through the semester. Goodbye for now.